let's take a look at our Hamilton practice set 1. All right. The number of edges in K10. So remember that to find the number of edges, we do n times n minus 1, and then we divide that by 2. So we can do that in our calculator, or we can absolutely just say, oh, well, that's 10 times 9, that's 90, divided by 2 is 45. So our answer is B. The number of Hamilton circuits in a K10. Now that is going to be n minus 1 factorial. 10 minus 1 factorial. Now, 10 minus 1 is 9, so it looks like my answer is A. N factorial. How do we find that? Well, typically that's n times n minus 1 times n minus 2, etc., all the way down to 1. However, because that would be kind of weird looking, we could always say, let's write it counting up instead of down, 1 times 2 times 3 times 4, etc., until we reach n, in which case it would be D. All right. How about 75 factorial divided by 74 factorial? Now, you can absolutely do this in your calculator. 75 factorial divided by 74 factorial. Thinking through it though, we're looking at 75 times 74 times 73 times 72, etc. divided by 74 times 70. Wait a minute. In multiplication, things cross out when they're in the numerator and the denominator. So 74 would cross out, 73 would cross out, 72 would cross. Everything crosses out except for 75. So the answer would be 75. And you can just really quickly take a look at that on your calculator. 75 math, PRB, 4, divided by 74 math, PRB, 4. All right. In a complete graph with 12 vertices, what is the total number of Hamilton circuits, including mirror image circuits, that start at vertex A? All right. Well, I know that n is 12. So 12 minus 1 factorial will tell me the total number of Hamilton circuits, including mirror circuits. Well, 12 minus 1 is 11, so we have 11 factorial. Number 6. Oh, there's the answers. We'll check those in a minute. The following circuit, or the following graph, does it have no Hamilton circuits, have several Hamilton circuits, all of which include the edge AG, have a single Hamilton circuit and its mirror image, several Hamilton circuits, none of which contain BD, or none of the above? Let's see. Just a regular random Hamilton circuit here works. That cannot be the only one. Let's see. I'm going to see if I can make one that contains BD. Yeah. I can get BD, so it's not D. It's not a single one. It's not no. All right. But every single one is going to have to contain AG, and it's going to have to contain FG because of those are the only two ways to get to G. So our answers are B, A, D, C, C, B. B, A, D, C, C, B. Right on. Let's go to the next page. For each of the following graphs, find all Hamilton circuits starting from A. And mirror images count as a different circuit. Okay, so I can go A, B, E, D, C, A. Okay, that's me starting going A to B. I'm going to move this up here so I can get a different color. I can go A, C, D, E, B, A. I could go A, D, and from here, I could go to E. No, I can't, because then there's no way to get back to C. So I've found the only two. Yep. Now, with this one, A, B, C, D, E, A. All right. A, C, D, E, B, A. A, D, E, B, C, A. All right, so we got those. And then A, B, E, D, C, A. That'll work. So we've got the two that go A, B, and there's two that go A, C. I should have done these in different colors. Let's see. Let's try that. All right, so here was the first one, A to B to C to D to E to A. That was the first. Then I could have gone A to B, then over to E, D, C, A. There's no other way for me to go if I go from A to B, so we're going to switch from A to C. So A, C, I could go B, E, D, A, or I could go A, C, D. Is that the way I just went? No. E, B, A. Or I could go A to D, C, B, E, A. A to D, E, B, C, A. And then, of course, I'm running out of colors. I can go from A to E, B, C, D, A. And I can go from A to E, B, C, D, A. Woo! All right. That's a lot. Graph 3. A, B, C, D, E, A. And then I can do A, B, D, C, E, A. But I'm always going to have to go from A to either B or E. And that's the only way I can get back So that's all I can do from A to B. Now let's go from A to E. A, E, nope, can't do that. Let's go A, E, D, C, B, A. And then we'll go A, E, C, D, B, A. And there's just those four. Now, finding all Hamilton circuits in a figure is a little bit tedious, and it's going to take some time, and you might go the wrong way. That's okay. Just take your time working through it. As we kind of work our way through this, we're not going to be as concerned with making sure that we do every single one, especially when we get into traveling salesman problems. We'll look at ways that you can find an optimal circuit or an approximate circuit without having to check all of them. All right. Oh, we were supposed to do other things. Are there any edges that must always be used in the circuit? All right. Let's actually, I'm going to change my color back to the one I like. Okay. So here, are there any edges that must always be used in the Hamilton circuit? So, of the two circuits that we found, what had to be used? Well, if you look, AB had to be used, BE, DC, and CA, because we only had one circuit and its mirrors. So every single one of those edges had to be in the circuit. Now here, we went everywhere. We went all over the place. So there was no edge that was used in every single graph. And then here, like I mentioned when we were doing it, AE and AB had to be in every single one because they're the only sides that connect to A. Last but not least, let's find a Hamilton path from C to E. All right, I'm going to follow the C to E here. We can go C, D, A, B, E. That'll work. From C to E here, we can go C, B, A, D, E. And here we can go C, D, B, A, E. And that's how we would get from C to E via a Hamilton path. Okay. Does a Hamilton circuit or path exist? So for each of these, we're going to see if we can find a Hamilton path and a Hamilton circuit. All right, let's take a look at this one. I can easily find a Hamilton path. However, if you look, there's no way for me to get back to G. So there's a Hamilton path here, but not a Hamilton circuit. And you're going to find here that we're dealing with the same thing. A Hamilton path is easily found, but a Hamilton circuit, there's no way for me to get back to A from D, or back to D from A. Here, B, A, C, D, or E, D. So right there, I've got a Hamilton path, but question, can I find a Hamilton circuit? Well, let's see if I do it a little bit differently. C, B, A, D, E, C. Yes, I can find a Hamilton circuit. Now, here, A, C, E is not the way to go. What if I go A, D, F, C, Nope, that's not the way to do it either. Now, do you notice here that there's no way for me to get to every single one without having to retrace my steps? And that's because no path exists and no circuit exists. All right. Good job, guys. I will see you next time for exercise 2.3. Have a good one.